Hello Math 152 students. In this video, we will take a look at some StatCrunch examples for 6.1 as well as some vocabulary issues. The first thing I want to point out is some definitions in your ebook. Chapter 6 has some new vocabulary and some new notation, some new letters and symbols associated with our concepts. But really what I want you to understand is we're putting some new vocabulary to concepts we already understand really well. So your book kind of lists a definition here that sounds a little bit cryptic. They tell you a random variable is a numerical measure of the outcome of a probability experiment. So its value is determined by chance. Random variables are typically denoted using capital letters such as capital X. What I want to do is take a scenario from chapter 5 that we understand and apply these definitions so we understand the context. So let's say we have a probability experiment, such as rolling a single die. That's an experiment because when we roll the die, we don't know the outcome. In other words, the value of what we get is determined by chance. So when we talk about a random variable, we could talk about the capital letter X representing the outcome of a roll of a single die. Then the values associated are 1 through 6. So when we say the capital letter X, that's the sort of description. We could say capital X is the outcome of rolling a die, and then we use the letter little x for the actual values. So you'll notice in your ebook, they go on to tell you the values are the little x's, 0, 1, or 2, or in our case, 1 through 6. Now, thinking back to the rolling of a single die, each of these values is associated with a probability. And in the single die roll, each outcome is equally likely and had a probability of 1 over 6. Now, just as a note, StatCrunch hates, or I should say, does not know how to interpret the slash with fractions, so we're not really going to be able to do much. I just want to show you an example that relates back to our chapter 5. In other words, StatCrunch likes it when you make probabilities decimals and not fractions. So the notation that we're going to use here is probability, but instead of just calling it probability, we write P of X, the probability of the associated X value of our random variable. So what I have here is a table that represents the outcomes for a random variable and the associated probabilities. We're going to be analyzing these sorts of tables in 6.1. Now, most of your examples are not going to have equally weighted probabilities, and that's where things become a little bit more complicated and a little bit more interesting. Now, you also have some other vocabulary involving discrete and continuous, tying in some examples in vocab from chapter 1. So some of that will look very familiar. So the next thing I want to do is take a look at an example in your book and show you how to do some stuff with StatCrunch. So we're going to look at example 2. Now, I do encourage you to watch these videos. Some of these videos, though, describe the general concepts. This particular video doesn't go over the specific example. So let's take the context for this table, make sure we understand. So suppose we're looking at a basketball player who's shooting 3 free throws. Sorry about that, guys. And let the random variable X represent the number of shots made. So if we shoot 3 free throws, we could make none of them, 1 of them, 2 of them, or all 3 of them. You can't make more than you shoot, and you definitely aren't going to get a negative number. Now, we have our little x values here and the associated probabilities. Now, where did these probabilities come from? These probabilities would have to be gathered from some sort of long-term model. In other words, these are usually provided for you, or in the case of the roll of a die, you might have a way to determine them from theoretical outcomes, like 1 out of 6 chances. However, for this particular player, this is telling us If he shoots 3 free throws, the probability that he makes none of them is only 1%. The probability that he makes 1 out of those 3 is 10%. The probability that he makes 2 out of those 3 is 38%. 3 out of those 3 is 51%. Meaning, he's not a bad player, right? 50% of the time, he makes all 3 free throws. Now, if this were a probability distribution for me, my probability would be probably 50% or more in the 0, and smaller probabilities for the 1, 2, and a pretty non-existent probability for 3. I'm not a basketball player. But what we would need to get these probabilities is some data. In other words, we would need lots and lots of data on how this basketball player performed in order to analyze the probability of making 0, 1, 2, or 3 out of our 3 free throw shots. So what we want to do is figure out how to visualize this in StatCrunch. Your book goes on to describe some rules. You do want to read over those, and we'll jump to StatCrunch in just a minute. Just like our probability models, our probabilities need to sum to 1, and we need to have our probabilities not be negative and not be greater than 1. Think about these as between 0 and 100%. So that's something you want to verify before you start putting your model into StatCrunch and using it. If these don't sum to 100%, or 1 in this case, you're going to have some issues. So I went ahead and just typed my table into StatCrunch, and I want to show you how to create a graph, and then we'll look at means and standard deviation. Scroll back up here. And you're going to choose your stat option and then calculators. Now, StatCrunch has a whole lot of probability models that are pre-done. We'll take a look at some of these in coming chapters, but you want to select the custom option. This is a custom probability distribution that we've entered. Our values are in the X column, and our weights or our probabilities are in the P of X, or second column. Don't need to worry about this, and just hit compute. Notice StatCrunch creates almost like a bar graph, not quite bars, but it creates a plot for what's going on. Your book discusses this plot further in the chapter, but it doesn't point you to the StatCrunch creating it. The other thing I want to point out is this mean and standard deviation. So we'll talk about that in a little bit as we go back through our ebook section. But for this part, what I mainly want you to see is that you can create a graph, visualize what's going on, and then you can also do some clicking. It's not letting me do it right now, but depending on, I think in other times you can click these. I'll have to see why mine is not letting me click. But then it also gives you the mean and standard deviation, which we mentioned. Your book goes into great depth on how to do these by hand, but I want you to be aware that you can input it into StatCrunch and calculate it automatically. So let's go ahead and go back to our ebook. So let's pick up with this example in our ebook. And your book does a little bit of examples, shows you that graph. And then I want to skip to the mean of a discrete random variable, because we saw that StatCrunch provided us that mean. And I want to show you what the book is doing by hand and how to tie that in. So the first thing to notice is that instead of just saying the mean, they use this mu sub x. So the mu is our, think about it in terms of our previous chapter as the population mean. But instead of just population here, think about it as the theoretical mean of our random variable. Notice they have the sub x, so it's the mean of our random variable. And they give you this definition that it's the sum of the x's times the p of x's. And the by hand calculation is actually not bad in this case. It's worth going through, but then it's also going to match our StatCrunch. So what this means is when we're looking at a random variable, we have our values and our probabilities. The probabilities serve as weights, and if we multiply our values times our weights and add them up, it gives us a weighted mean. So notice this example just tells us we multiply our values in our two columns and add them up. So we weight our 0 free throws by 1%, 1 free throw by 10% of the time, 2 by 38% of the time, and 3 by 51% of the time. That gives us a mean of 2.39 approximately, which if you notice is exactly what StatCrunch gave us. Now, just like all of our standard deviation calculations previously, you want to use StatCrunch. I'll come back to this interpretation in a minute, but I want us to look at just the book's version of how to do standard deviation by hand. Notice your book gives you a giant formula, and then they show you how to do it two ways using tables. Okay, it's not too bad, but it's a little bit unnecessary. What I want to show you is that if you want to find the standard deviation, it requires that you know the mean, and then requires that you do a lot of work. In StatCrunch, you basically have to just click, right? So StatCrunch will tell you the standard deviation, see 0.7056, which notice they didn't include all the decimals, but is exactly matching up what we would do by hand. So anytime you're doing standard deviation, definitely do StatCrunch, and then means I would recommend practicing a few by hand and checking with StatCrunch so that you feel comfortable with both. Okay, so let's go back and think about a little bit of the interpretation of that 2.39. If we're thinking about our table, we already said that most of the time our player makes between 2 and 3. So this average that we're getting, or the theoretical mean, is saying that over the long run, we're going to have an average of 2.39, 2.4 free throws out of every 3. Now, if a player goes and takes 3 shots, there's no way he can make exactly 2.4 free throws. This is, you can think about it, a long-term average, what we would get if we did this experiment many, many times. Now, I want to contrast this with the concept of X-bar. Your concept of X-bar gets a little bit confusing because we're using X-bar to mean the mean, but we mean it in a different way. So instead of thinking repeated experiments, let's say I only do 5 experiments. So when I say 5 experiments, let's say I shoot 3 free throws 5 times. In other words, 5 repetitions of our 3 shots. And let's say that I'm having a terrible day, or our player is having a terrible day. Okay, and he decides, or he gets 1 free throw out of each of those 5. Okay, so let's say he gets 1 5 times. So out of those 5 repetitions, his average was 1, a very easy average. And that meant that he was having a bad day in comparison to what we would expect. Oops, put these in the wrong one here. Meant to put it up here. Wait, just to kind of keep it on the same page. So let's say we had our series of 5 experiments, each where we made 1 free throw. If we know that this player is expected to have an average of about 2.4, an average of 1 is pretty terrible. Now, let's say we repeated this experiment, and let's say we only did it 4 times this time. And on the first one, he got no free throws, and then he got 2, but then we're having another terrible day. No free throws, no free throws. His average for those 4 times was 0.5. We had 2 free throws and 0 on the rest. So just adding those up, we get 2 divided by 4 gives us 0.5. His average free throw was 0.5 on those 4 rounds. This idea of the 0.5 and the 1 in these 2 specific examples is an example of the X-bar, meaning the X-bar takes a specific number of repeats and finds your value for those specific ones, whereas your mu sub X-bar, or this theoretical mean that we were discussing up here, takes into account the probability distribution and long term. So you want to be careful with